Hello, everyone, and welcome. This is a sustainable IT and sustainable AI practitioners playbook for AI era. I am Dr. Niladri Choudhuri, President of Green Computing Foundation and CEO of Excellentro. At Green Computing Foundation, we focus on the raising of awareness on sustainable IT and sustainable AI and help students, faculties, startups, MSMEs, corporates on their sustainable IT and sustainable AI journey. So, over the next hour or so, we are going to rewire how you think about building a software across DevSecOps, product development, and operations. This isn't a lecture about saving the planet in the abstract. It's a working playbook full of verified numbers and sources and practical moves you can take back to your team the next day. So let's get started. So, what we will cover today, here's the shape of our time together. The whole program is broken up into five parts. Part one is the state of play, the numbers, the definitions, the thinking lenses, and the regulatory landscape. Part two is the sustainable IT, the platform. Here we will talk about life cycle, green software principles, data centers, and hardware. Part three is sustainable AI, the workload. Here we are going to talk about where AI energy actually goes, the modest life cycle, and the economics of inference. Part four is the DevSecOps reframed for this era, pipelines, gates, metrics, roles, and ways of working. And part five, the last one, is the roadmap and the pact, a maturity model, patterns from the field, a 90-day plan, and the commitments you will take with you. Now, let us understand why this conversation and why now. Now, why does this matter? You can see the figures here. Data centers and AI workloads have moved from an edge case to the mainstream infrastructure cost, and we can measure it. In 2024, the global data center consumed about 415 terawatt hours of electricity, roughly 1.5% of the electricity of the entire Earth. The International Energy Agency's base case projects that more than doubles to around 945 terawatt hours by 2030. Growth has compounded at about 12% a year since 2017. It's not just energy. In 2022, the workload generated 62 million tons of e waste, and only 22% of it was formally recycled. Training GPT-3 alone evaporated an estimated 700 kiloliters of fresh water in US data centers. The latest UN survey report says that by 2030, AI will use up water that is required by 1.3 billion people. And the ICT sector as a whole accounts for somewhere between 4 to 6% or more of the global greenhouse gas emission. Now, here is the context that makes it real. Global data centers in 2030 will use roughly two-thirds of India's entire current annual electricity demand for one industry. That's why we are having this conversation. Later on, we will also see one more factor. We have been used to a more deterministic situation, and now with the AI era, it is a probabilistic situation. Let us look at the two terms, sustainable IT and sustainable AI. And these two terms are joined at the hip. Sustainable IT is the discipline of designing, building, running, and retiring the digital system so they minimize the energy, carbon, water, e-waste, and social costs across the life cycle, from cheap fabrication all the way to landfill. Its scope is everything: data centers, network, devices, software supply chain, end of life, the chip manufacturing, semiconductors, everything. Whereas sustainable AI is treating every AI system, from a tiny 50 kilobyte classifier to a frontier model as a resource consuming product whose business value has to justify its environmental and human cost. That covers training data, model selection, fine tuning, inference, prompt, design, agentic loops, and evaluation. We will go into details for each. A couple of quick numbers to make it concrete. On the IT side, simply stretching a laptop refresh from 3 years to 5 years can cut around 40% of the device's scope 3 emission over a decade because 85 to 95% of the device's life cycle carbon is from manufacturing. On the AI side, a 7 billion parameter distilled model on a narrow task can cut inference energy 8 to 15 times versus a 70 billion model with under 2% accuracy loss. So, to achieve this, we have to go through the three thinking lenses and drive sustainable AI and sustainable IT. It, the question is, how do we actually produce them? The answer is three thinking disciplines applied in sequence at every stage of the product. And all three has to be looked at, not just one. So the first is design thinking. Start with humans and the planet they live on. Build devices, interfaces, and infrastructure around real user needs, not feature creep. For AI, that means building the smallest model that solves the user's actual job. So the first thing is we need to understand what the user really wants. And sometimes user don't know what they want. So we have to understand together what they want. And that's where the probabilistic error comes into place. Second, critical thinking. Question every default before you encode it in silicon. Do we even need a new service, a new region, a new data store? Does this need a large language model, or will a rule or classical machine learning do the job? Whose data, whose carbon, whose risk? And the third is the computational thinking. That is how computers think or run. And we have to think that way to be able to make them work most efficiently. So decompose, abstract, pattern match, and decide. Use the cheapest correct algorithm, reuse, don't rebuild, route by complexity, and pick the smallest sufficient model for each step. Picture a team asked to add an assistant, AI assistant. Design thinking asks, what is the user actually stuck on? Do they really need an AI assistant? A critical thinking asks, does this need an LLM or a smart form? Computational thinking asks, can a 50-line rules engine solve the problem or 80% of the problem? Together, the three lenses produces sustainable IT and sustainable AI at the same time. We have to look at this entire stack. This is what you don't see in an invoice. Think of an AI feature as a stack. At the very top is the user experience. That's the visible 5%. Just below it sits your application and business logic, the code, the services, the APIs. Then it gets heavier. Inference compute, every call, every token dominates the cost of anything running in production. Below that is the training and fine tuning. Heavy but episodic. You don't do a training every day. Maybe once in a year, maybe once in 2 years, or maybe once in every half a year. Then data pipelines and storage, the silent multiplier. And at the very bottom, the invisible majority, hardware, water, and the supply chain, which is often 50 to 85% of the whole life cycle. If you cannot measure the layers below the API, you are not engineering. You are not guessing, you are just guessing in grain paint. Apple's own reports show that more than 80% of the MacBook's lifecycle emission are embodied in manufacturing. not use. The same shape runs up the whole stack. Visibility precedes responsibility. You must have heard about the triple bottom line: people, planet, and performance. Sustainability is not the opposite of performance. It is the discipline of getting performance without externalizing the cost onto people, water, soil, and the next generation of engineers. That's the triple bottom line. People, the worker conditions in the supply chain, the digital access. High cost AI may not be accessible by all, creating a digital divide. And inclusion, algorithmic fairness, and the cognitive load and well being of users. Planet, greenhouse gas emission across all these scopes: water consumption, e waste, circular materials, land use, the data centers creating the biodiversity loss. And performance, cost per outcome, reliability and uptime, speed and latency, and innovation velocity. You have not heard about productivity, because productivity automatically happens when all these work fine. So take one decision. Are you going to buy 350,000 laptops for all your employees? Performance lens looks at speed and warranty. People lens asks about the cobalt sourcing in the supply chain. The planet lens asks about the take back and refurbishment. And one decision, three lenses, and very different outcomes. We also have to look at the regulatory landscape. And now, with a lot of the business being diversified in areas like Europe, Australia, Brazil kind of places, and not just US. Sustainability is shifting from voluntary to mandatory fast. In EU, the Corporate Sustainability Reporting Directive, or CSRD, mandates ESG disclosure for around 50,000 firms. And the EU AI Act imposes obligations on high risk AI systems, including energy use disclosure. In the US, the SEC's climate rule and California's SB 253 and SB 261 require scope 1 and 2 and eventually scope 3 disclosure. In India, SEBI's BRSR framework is mandatory for the top 1,000 listed companies and covers ESG indicators, while DPDP Act of 2023 drives data minimization, which is sustainability lever in disguise. And globally, the software carbon intensity specification became an ISO standard in 2024, the first internationally recognized way to measure software carbon per functional unit. Now, here is the twist. An Indian SaaS firm serving you customers is now exposed to both BRSR and through the customer's value chain reporting, CSRD. Even with zero entities, ESG reporting is becoming a B2B contractual reality. Compliance is the floor, it is not the ceiling. Discipline is the differentiator. So we look at the frameworks that practitioners should know. Build on standards, not slides. You don't need to invent your own metrics. There's already a solid toolkit and auditors recognize it. The GHG protocol is the de facto global standard for scope 1, 2, and 3 accounting. ISO 14064 and 14040 cover greenhouse gas specific quantification and life cycle assessment. Green Software Foundation's SCI, now ISO 21031, measures software carbon per functional unit per release. And ISO 30134 gives you the data center KPIs like PUE and WUE. SASB and IFRS S2 covers the sustainability disclosure, with IFRS S2 focused on climate. And emerging task force frameworks address AI specific climate risk. So a practitioner's minimum kit is just four of these: GHG protocol for your accounting boundaries, SCI for software measurement, 30,134 for data center, and IFRS S2 if you are listed. Four standards, one coherent story. Use what exists. Don't reinvent local metrics that no one can audit. We have been talking about scope 1, 2, and 3. So let us just understand quickly what scope 1, 2, and 3 means. So let's make GHG protocol practical because this is where engineering actually lives. So there are three scopes as per the greenhouse gas protocol. Scope 1 is the direct emission sources you own or control, like backup generators, where you use diesel. Company vehicles, again, where you use diesels, not the ones that you have hired from others. That comes under scope 2. This one is your company's own vehicles. Or refrigerant leaks from cooling. That's typically 5 to 15% of the digital footprint of the company. Scope 2 is the purchased energy, the electricity, heat, and cooling you buy. That's where your grid mix lives and where renewable contracts apply, typically 10 to 25%. Now comes the big one, the scope 3. And this is very difficult because this is not within your control. It is everything else other than what is defined in scope 1 and 2. Your supply chain, your capital goods, your business travel, your purchase cloud services, your use of products you sell, and end of life. This is typically 60 to 85% of the footprint, and it's where most engineering decisions live. What you build, what you buy, what you ship to users. For a SaaS company, scope 1 and is the tiniest. Scope 2 is mid-size, and scope 3, the laptops, end user devices, travel, third-party APIs, embedded cloud hardware, that is the elephant in the room. Imagine companies are also going and saying, because of security reasons, you cannot use your company laptop for personal use. Your company policy is forcing people to have two laptops. Highest amount of carbon footprint is what? Embedded carbon. So that much more carbon footprint is happening. But that is used to be days earlier. Do you really need that now? No. Banks, European banks, big banks in the world, who has a lot of compliance to follow, a lot of rules to be followed, and they are very conservative. They have gone with bring your own device using virtual desktop infrastructure. So now let us look at how these three lenses that we talked about, design thinking, critical thinking, and computational thinking, produce sustainable IT and AI. So let's make that mapping explicit. Read this as a grid, each lens applied to IT in one column and AI in the other. Design thinking shapes the devices, infrastructure around real needs, a smaller IT estate, and longer device life on the IT side. The smallest model that solves the user's job on the AI side. Critical thinking forces the new services, region, or dependency to earn its place and forces the AI versus non AI decision before anyone writes the code. And computational thinking pushes the cheapest algorithm and the correct algorithm and reuse over rebuild on the IT side, and decomposition, complexity based routing, caching, batching, and quantization on the AI side. So the team that applies computational thinking systematically gets both outcomes, rehosting instead of rebuilding infrastructure and routing a query through a smaller classifier before every invoking the LLM. One discipline, two sustainable outcomes, not by accident. So now let us look at the sustainable IT platform in part 2 of this program. Let's make the mapping explicit. So this is the state of play. Now let's get into part 2, the sustainable IT and platform layer. We look at lifecycle decisions, green software engineering principles, and data center realities, and the hardware lifecycle that quietly dominates scope 3 emissions, the big part of it. The AI era is probabilistic and not deterministic. So, this is where the three lenses are non negotiable now. Classical software deterministic, same input, same output. Spec is the contract. Test is a simple pass or fail. Customers can describe what they want. Engineering means building to spec. An AI era system are probabilistic. Same input produces a distribution of outputs across runs, across models, across fine tunes over time. The spec is moving target because the model itself is a part of it. Testing becomes statistical, accuracy, drift, fairness, hallucination, and customers can't fully specify what they want. They learn what they want by seeing prototypes. Earlier, you had a standard financial accounting system, but in today's scenario, in a probabilistic scenario, you have things like decentralized finance, DeFi, or regenerative finance, which is ReFi, which is much more probabilistic, which is not that fixed debit and credit kind of scenario. That itself is there, but there is a lot more to it. So picture a bank building an AI assistant for their advisors. 3 weeks of prototype reveals that the advisors don't actually want answers. They want their hesitation reduced before a client call. That real requirement only became visible after probabilistic prototypes for a few times, showing what was possible. Engineering for probabilistic systems requires thinking, not just specifying. And that's where people needs to go beyond just coding, to have that capability of design thinking, computational thinking, and critical thinking. So, green software in engineering, the working principles here. How do we engineer for the grid? There are 6 working principles adapted from the Green Software Foundation. The first is energy efficiency. Do the work in fewer joules. Joules is the measurement of energy consumption as per any of the ESG disclosures that is required. Through better algorithms, languages, and query plans. Hardware efficiency. Use less hardware for more work with shared multi talent refurbished fleets. Carbon awareness. Schedule heavy work where and when the grid is cleanest, because carbon intensity is the signal you can act on. It is called demand shifting. Network efficiency. Move less data, cache, compress, and co-locate. Measurement. If a workload isn't measured for energy and carbon, it cannot be improved or defended. And climate commitment. Reduce first, then reuse, then renew. Offsets are the last resort, not the first headline. Offsets means you do power purchase agreements, which is an offset, or carbon credit, that is an offset. But that does not reduce your carbon footprint. It's just accounting. So we need to reduce what we are doing. Carbon awareness in practice. Tools like electricity maps, watt time, expose hourly grid carbon intensity per region. Move a nightly retraining job from a coal heavy hours to the solar peak, and you can cut carbon by around 40% with zero code change. You don't have to do all your work in one region. Now let us look at the SCI. Let's anchor one metric, software carbon intensity, or SCI now, ISO 21031. The formula is SCI equals equals energy times carbon intensity plus embodied emission, all divided by a functional unit, a request, a transaction, a user session, an asset, means a compute asset. 4 things make it powerful. First, it's a rate, not a total. So it scales with usage and is comparable across releases. Second, it includes embodied carbon, the carbon spent making the hardware, which is usually ignored and often dominant. Third, it rejects offsets. Only real reductions count. And fourth, it's now an intentionally recognized auditable ISO standard. So a quick worked example, an API service runs 40,000 requests per release using 1200 kilowatt hours on a grid at 180 grams of CO2 per kilowatt hour with 60,000 grams of embodied emission. Run the numbers and you get 6.9 grams of CO2 per request. Multiplied by 4,000, you get the total carbon footprint for every release. So, like that, you can calculate for everything. Now, let us get into the data center realities. Now, either you are using your own data center or you are using cloud. Now, cloud also is not cloud per se, it is somebody else's data center. So, where does our workloads actually live? Three numbers decide the data center: the PUE, or the power usage effectiveness. It's the total facility power divided by IT equipment power. The industry average is 1.55. However, many governments like Singapore have said that you have to be efficient enough to be 1.2. The best hyperscaler hit around 1.10 WU, 1.10 PUE. Water usage effectiveness WUE is liters of water per kilowatt hour. The hyperscaler median is about 0.18, but it varies tenfold by region, and the grid mix carbon intensity ranges enormously. India was around 700 grams per kilowatt hour. Now it has gone down a little bit, but still not that much. The US around 370 and EU around 250, and the Nordics as low as 30. So here's the practical lever. Region selection alone can change a workload's effective carbon by 10 to 25 times without touching a line of code. Run a 4-hour nightly ETL job in US East versus the same job in Sweden, and you get roughly 15 times lower carbon for identical code. Egress costs and data residency rules constrain this, but the lever is real and it is sits upstream of all your other optimization. In India itself, if you look at the grid mix of West, around used to be around 750, and if you look at the grid intensity of South of India, it is around 600, and if you look at Himachal, it is around 14, right? So different places, difference is there. Now let us look at the hardware life cycle, the scope 3 you cannot hide. So it starts from the chip to the landfill. Six stages. One is mining and making, raw materials, semiconductor fabrication, about 2,200 gallons of ultra pure water per chip. Assembly and transport. Two, procure right sized, long warranty, repairable, and certified refurbished options. And that's where you need your products to be modular. So you are able to change part of it. You don't have to throw away the whole thing. Three, operate, power management defaults and firmware updates. That is important because if there is too much of frequent peak loads and off peak loads, the hardware has an impact and the lifespan gets reduced. Refurbish. Four, the maintain the battery swaps, parts replacement, and security patches. Five, refurbish. Internal redeployment first, then certified third party programs. And finally, recycle certified e-waste channels like R2 and e-stewards. Remembering that 22% global recycling rate is the floor, not the goal. It is very, very low. The headline fact: smartphone production in it is 85 to 95% of its life cycle carbon. So doubling a device life roughly halves the annualized footprint. A 50,000 person enterprise that move laptops refresh from 3 to 5 years can drop annualized device emission by around 40%. Save 20 to 30 million in capex with employee satisfaction unchanged. And as I said, if you go into bring your own device, it further does it. So now, after making, we get into the sustainable operations. Run less, run smart. Operations is where bills and carbon compound. So let's run less and run smarter. Four practices: carbon aware scheduling or demand shifting, defer batch and training to low intensity windows, and route inference to cleaner regions where latency allows. So we are talking about demand shifting in terms of geography and demand shifting in terms of timing of the day where the grid is green. Right size infrastructure, match the GPU or CPU class to the workload, consolidate idle capacity and use spot, shared, and serverless where it's safe. Data hygiene as an ops practice, tier, archive, delete, old data still burns power and creates risk. And the hardware lifecycle, refurbish and reuse, over refresh and replace. Plan end of life from day one because e-waste is a design flaw. So a bank moves from a nightly batch from a fixed 2 a.m. start to a flexible 4-hour carbon aware window. Same SLA, 30% lower carbon, no architecture change. Lever was the scheduler, not the code. Sustainable operations is just reliability engineering, broadened reliability of resource use, not only uptime. So FinOps is a powerful sustainability lever because cloud cost and carbon are highly correlated. Both grow with compute, storage, and data transfer, but there are caveats. FinOps with GreenOps is what is best. Only FinOps doesn't work. For example, FinOps, looking from the cost point of view, might go into reducing cost by going into a more longer commitment contract. It doesn't change the carbon footprint. Less use, optimizing your resources is what is going to change, right? So where they align, right sizing instances, auto scaling, shutting down idle resources, caching to avoid redundant compute, and choosing reserved or spot instances over always on demand cut the spend, and you usually cut the carbon. Where they diverge, this is important part. Cheap regions are sometimes coal heavy. Egress can be cheap, but it is always carbon positive. Renewable certifications lower your reported scope 2 without changing the real grid. The serverless cold starts can mask embodied carbon. So a FinOps audit kills $400,000 of idle EC2 capacity and saves about 250 tons of CO2. A clean win. But moving backups to a cheaper, coal heavier region saves $80,000 and adds 30 tons. Both have to be checked. Now let us look at your supply chain. Scope 3 in practice means your supply chain is your carbon. Let's walk the relation. Hardware vendors demand product carbon footprint data, recycle content disclosures, and take back program, and negotiate longer warranties. Cloud providers use their carbon footprint tools, compare location based and market based emissions, and question region shifting recommendations. SaaS dependencies, every tool you adopt is your scope 3. So audit your stack annually and consolidate the overlaps. We are not only talking about the supply chain of your hardware, we are talking about the supply chain of your software too. When you are taking open source products or any tool or anything, sponsor maintainers of efficient libraries and choose ones that publish energy benchmarks. Contractors, their travel, devices, and cloud usage are yours too. And customers downstream your defaults like video quality, autoplay, or model size shape their footprint. And that's where we have the concept of demand shaping. Every time you don't have to give the best of the quality. You can go to lower quality. Where they need, the customer specifically needs higher quality is when you give it at a higher cost. The CSRD angle again, an Indian software firm with EU customers will be asked for its scope 3 numbers to feed those customers' own disclosures. Vendors who can produce credible numbers will win renewal. Those who can't will lose it. And I think you are already seeing this as points that you have to mention as response to the RFPs. So how do we navigate the probabilistic ambiguity lens by lens? So, scope 3 in practice means your supply chain is your carbon. Let's walk the relationship. Hardware vendors demand product carbon footprint data. We have all seen this. So, now how do we navigate the probabilistic ambiguity? So let's see how the three lenses become operational against the specific problems. Problems of probabilistic systems. Each lens solves exactly one, and only together they do the work. Design thinking solves the problem that customers can't articulate what they want. So you prototype as conversation, observe real workflows, and treat requirements as hypotheses, not contracts. Critical thinking solves the problem that probabilistic outputs look plausible, whether or not they are correct. So you question every output source and confidence and defend against the confident wrongness. Computational thinking solves the problem that these tasks resist single model solutions and sprawl in cost and latency. So you decompose into small testable steps, root by complexity, and bound in iterations. Customer says build an AI to write code. Design observes that developers spend more time understanding existing code than writing new. So it reframes into a code comprehension assistant. Critical validates output against test suits, not vibes. And computational decomposes it into retrieval, small model summarization, and LLM only for synthesis. Three lenses turn a vague brief into a defendable, sustainable system. So, for the same system, you can understand now that we are talking about that for the whole thing, you don't need to have only one model. You can have multiple models of different sizes for the same work at different levels. Now, let us go into the part three, the sustainable AI, the workload layer. We look at where AI energy actually goes, the decisions across the life cycle, the inference economics that dominate lifetime cost, and the anti patterns that are specific to this era. If you see this chart, where is the biggest one? You see that training is the headline. Everybody talks about training needing a lot, but where is the biggest bar? The inference. So read this one carefully. Training is the headline, inference is the bill. A model is trained once or twice, maybe in a year, or even four times a year. Then it runs millions of times. So optimizing the runtime path, model size, prompt length, caching, routing usually beats the optimizing the training run. Brookings reported in 2025 that 80 to 90% of the computing power used for AI comes from inference, not training. To put numbers on it, GPT-3 training used about 1,287 megawatt hours and emitted around 552 tons of carbon dioxide. But 2 years of GPT-3 class inference at scale exceeds the training energy several times over, which means a 20% inference optimization outweighs a 50% training optimization. Spend your effort where the energy actually is. And that's where we are talking about use CPU based inferencing, not GPU based. And nowadays, the CPUs are much more capable with the matrix multiplication capability, much stronger than GPUs. Now, sustainable AI across the model lifecycle. Here, where the choice compounds across five phases of the model lifecycle, each will with a critical question and a sustainable default. So, we are talking about problem framing, which does this even need AI is the first question to ask. The why. Pick the smallest tool that fits a heuristic, classical ML, or an LLM, a small SLM, or a notebook LLM kind of. The data, what's the minimum useful data? Less the better. Governed data beats more data. Model selection, building, fine tune, or call. Prefer smaller, distilled, open, shared models. Inference, how often, how rich, how fast. Cache batch, root by complexity, and use the cheapest sufficient model. And evaluation, what does good enough look like? Stop training when the curve flattens. You must have heard I am talking about caching a lot. Google says that in a search, 80% of the search is of the same thing. So when you are asking questions to the model, a similar trend works. May not be 80%, but a lot of it is the same question being asked by different people or different systems. There is a lot of repetitive questions, and those can be better handled with cache without trying to process an inference in a model. The compounding effect is huge. Replacing a 70 billion parameter model with a 7 billion fine tuned one on narrow task can cut inference cost and energy by 8 to 15 times and under 2% accuracy loss. Usually invisible to users, and that choice repeats across every single call. So sustainable AI and sustainable is not about anti AI, it is intentional AI. So let us look at problem. Now we'll go deep into each. Let's look at problem framing. Now, phase one of problem framing is the highest leverage decision you will make because it happens before any code is written or any model is selected or any data is being processed. The question that prevents most waste: does this problem need AI at all? Think in tiers. If a rule covers 70% of the cases, write the rule. For tabular structured data at modest scale, classical ML is the best. Gradient boosting, logic regression, random forests, they have tiny footprints and often higher accuracy. And we have seen this in practice when we have done the hackathon called Green Mind Hackathon from Green Computing Foundation, where more than 1,500 participants participated from India and abroad. And this is exactly the result we got. For most enterprise language tasks, small language model under 7 billion parameters often fine-tuned runs on a CPU or modest GPU. And frontier LLMs only when the task genuinely needs broad world knowledge or open-ended reasoning. They are expensive, make them earn their place, like drug discovery. So a telco proposed an LLM for classifying customer intent. A simple logistic regression on call metadata hit 91% accuracy at 1/10,000th of the inference cost. The LLM is now reserved for the 9% of genuinely ambiguous cases. Match the tool to the problem, not the problem to the tool. Data minimization. Data is a big area of carbon footprint and energy consumption. Data minimization, every data set has carbon, water, attention, and risk attached to it. The smallest data set that solves the problem is also the cleanest, safest, and the most defensible. What we have seen is that data is not clean in most of the cases. We have already learned garbage in, garbage out, but now it is garbage in millions and trillion times garbage out. Curate, don't hoard. 10,000 good labeled examples often beat a million noisy ones. At 100 times less compute, deduplicate aggressively. Pre-training datasets often have over 30% duplicates, and removing them saves training carbon directly. Apply retraining windows, old data cost storage, backup, and security attention. Embed governance early, DPDP, GDPR, sectoral rules, privacy minimization is data minimization, is energy minimization. Share, don't replicate. A shared feature store stops the same embeddings between being computed 5 times. And audit synthetic data generation is also compute too. A pipeline found 38% new near duplicates in the 800 billion token corpus. Deduplication saved roughly 38% of the training compute and on the next run, and with no quality change. The paid for the dedupe pipeline 20 times over. DPDP, GDPR, and sustainability all ask the same question: do you really need this data? Then comes the model selection. Model selection is not the first thing. Model selection, build, fine tune, or call. Think of it as the three rungs on a ladder and start at the top. First choice, call an existing API. No training costs, provider amortizes the infrastructure carbon, and you iterate first. The trade offs are per token cost, data leaving your boundary, and vendor lock in. Second choice, fine tune a small open model. You get 10 to 100 times lower inference. Your data stays in house and an open license. At the cost of some training compute and the ML ops maturity to do it well. And the third choice, train from scratch. Only when the first two genuinely don't work, train from scratch. Maximum control and domain specific gains, but very high training cost. Deep expertise required and it's carbon intensive. To size it, training GPT-3 emitted about 552 tons of CO2. Distilling to 7 billion and fine tuning on a narrow task is roughly 5 to 20 tons. The gap between the rung 2 and rung 3 is often 30 to 100 times of your lifetime. Again, choose the models. You can use multiple size models for different things for the same work. Phase 4, inference optimization, is where 60 to 90% of the AI lifetime cost lives. So this is where engineering discipline really pays off. The six techniques are there. The first is the cache aggressively. For identical or semantical similar queries, a 20 to 40% hit rate is common. Route by complexity, cheap classifier first, small model for 80%, the large model only for the hard cases, and batch where possible. Many providers often offer 50% batch discounts. Quantize and distill. Like instead of float, you can use int 8 or int 4 quantization, and knowledge distillation gives 2 to 4 times the throughput at the small quality cost. However, make sure that quantization does not reduce quality. Limit context and tokens. Tight prompts, capped retrieved context, hard output limits, and use streaming with early exit. Stop when the answer is complete. Don't pay for 500 unused tokens. A search team added semantic caching with a 5-minute window on a similar queries. 35% of the inference simply disappeared. Latency improved on cache hits, and the quality was unchanged. The implementation, one engineer for 2 weeks. Evaluation discipline. Without a defined finish line, training will always burn more carbon. Evaluation turns good enough from a feeling into a number. Define the bar before training. Target accuracy or F1 or win rate in writing and stop when you reach it. Watch the loss curve. The marginal gain per epoch flattens, but with the next epoch costs the same as the first. Use a holdout set, not train loss. To see the real plateau, track uh, cost very well. Dollars and joules per percentage, point of accuracy gained, reuse benchmark, suits like MMLU, MT bench, or Helm, and run continuous eval in production so drift triggers retraining only when needed, not on calendar. A vision team trained a defect classifier to 98.2% F1 at epoch 12. They pushed 8 more epochs to reach 98.5. The zero point 0.3 point gain cost as much GPU time as the entire first 12 epochs and barely shifted production outcomes. Know when good enough is good enough. What are the metrics, AI specific metrics that matter? Beyond accuracy, there are six AI specific metrics worth watching. Tokens per task, the cleanest signal of the prompt and agent waste, cost per outcome, per resolved ticket, completed transaction or accepted suggestion, carbon per inference, SCI applied to the inference path, tracked per model and region, cache hit rate, direct lever on cost and energy, tail latency at P99, where your caching and routing trade-offs surface, and the drift score, which triggers retraining only when it's actually needed. A support assistant cut tokens per resolved ticket from 4,200 to 1,400 just by tightening prompts, trimming retrieved context, and capping output. Same customer satisfaction score, roughly 3 times lower energy and spend per outcome. Don't track everything. Pick three, measure relentlessly, and decide on evidence. In your own work, have you ever given an instruction in the prompt to not give commentary and give only the final question, the questions relevant and the final output? You will be able to do more work using the same token limit that is there, as opposed to what it would have done while it was giving the commentary. So, what are those AI era anti patterns to retire? Some habits becomes comfortable but costs you dearly. So, first is AI by default. Reaching for an LLM where a rejects, a rule, or a query would do the job at a thousandth of the cost. Bigger the better. Choosing the largest model for prestige, not because evaluation requires it. Always on agents. Long running loops that retry, reflect, and reason past the point of useful work. Actually, you should also have a end of life cycle for your agents and APIs and everything. Data hoarding, collect and keeping data without a purpose while risk and burn compound silently. Greenwashing dashboards, carbon charts nobody acts on, and offsets framed as reductions. And refresh cycle thinking, replacing hardware on the calendar instead of the evidence. On always on agents. One research agent was found running self reflection loops 24 by 7 across hundreds of dormant tasks, burning compute equivalent to a small office and helping no one. A hard iteration cap is one line change with outsized impact. Most waste in the AI era is habit, not technology. So now let us look at part 4, which is DevSecOps reframed for the AI era. Let's make this operational. We'll reframe DevSecOps from the AI era, the pipelines, the gates, the metrics, the roles, the ways of working, not separate ceremonies, just sharper ones. So we start with the DevSecOps reframed. So the core idea of speed, security, sustainability are no longer trade-offs. They are the same engineering discipline expressed at such different layers. Let's take the three layers. If you look at resilience, resilience also comes with sustainability. Build in the dev, build deliberately. Right size the problem before the model, reuse components, question every new service, run carbon aware design reviews. In sec, secure the model and the planet, treat data weights and prompts as assets, threat model AI supply chains and AI related threats, not just code. And remember that privacy is a sustainability lever, because less data means less burn. And in ops, run with feedback. Make carbon and cost first class SLOs. Auto scale on demand and on grid intensity, and decommission ruthlessly. In practice, a design review rejects a new microservice in favor of an existing one. The red team treats a prompt template as an asset, and an SLO breach when carbon per request raises 20%. Treated exactly like a latency breach. Or one loop, three responsibilities. A sustainable DevSecOps pipeline. Here is the pipeline where every gate earns its keep. 8 stages: plan with carbon aware story shaping, code with lint and green code patterns, build with reuse, caching, and minimized images, test with energy and performance tests, secure with AI supply chain threat modeling, release with carbon aware deployment, run the right sized auto scaling, and observe watching carbon cost and SLOs. So observability should bring the carbon cost, water, all sustainability related aspects, all of it wrapped in continuous feedback. Three principles tying together: shift green left, move sustainability decisions into plan and code, not just run. Policy as a code, even sustainability policy, carbon and data minimization rules live in the pipeline, not in slide decks. And two-way telemetry, production signals feedback into design choices and team OKRs. And concretely, a build gate fails CI if a container image exceeds 800 megabytes, for example. A release gate throttles deployment during high carbon grid hours unless they are tagged time critical. And both were implemented in one sprint with one off the shelf tooling. Every stage is chance to spend less on the planet's budget. And this will also ultimately reduce cost and improve profitability. How the three lenses change the way of working. Let's compare before and after by lens across the practices you already run. Same rituals are sharpened. So we look at the discovery and sprint planning. Through the design lens, instead of building what was asked, you observe the real job first. Smaller scope, smaller estate, smaller models. Architecture review through critical thinking beyond performance and security. You question every new service, region, and dependency, and decide AI versus no AI before model choice. And data management through critical thinking. Instead of collect now, decide later, you collect with purpose, retain with policy, and delete on schedule. Build an implementation through computational thinking. Instead of throwing the latest tool at it, you decompose, use the cheapest correct algorithm, and route by complexity. Definition of done through all the three, not just work, test, pass, secure, but lenses applied and within carbon and cost budget. The incident reviews ask a new question: which lens did we skip? And what did we burn that we didn't need to? So, what are the metrics that matters? What should the practitioners actually watch? Six metrics span the platform on the workload. SCI, the software carbon intensity, grams of CO2 per functional unit. That's the first one. PUE, the data center efficiency. Industry average 1.55, as I said, now it is going more towards 1.2. WUE, water per IT kilowatt hour, critical for AI workloads, cost per outcome, which aligns engineering, finance, and sustainability. Tokens per task, the cleanest waste signal for LLM workloads, and MTTRG, the time to fix a sustainability regression. Uh, Culture metric borrowed from site reliability engineering. Don't boil the ocean. A minimum viable starter set is SCI for one production service, cost per outcome paired with it, plus tokens per task if there is an LLM in the loop. Three numbers reviewed weekly at OKR grade. Most organizations never get past one. So pick a small set, measure relentlessly, and decide on evidence. Now, we always have to give accountability and responsibility to, to the roles. Otherwise, nobody is responsible, nobody is accountable. So, discovery and sprint planning through the design lens instead of building. So, who owns that? Sustainability is everyone's column on the RACI. Let's give each one a role. So, product manager frames the outcomes, not features, and defines the question: do we need this at all? The architect chooses the lightest fit for purpose stack and justifies every new service. The developer writes efficient code and reuses over rebuilds. The ML or the AI engineer right sizes the model, optimizes inference, and stops training when value plateaus. The security engineer threat models AI supply chains and treats privacy as efficiency. The SRE or platform engineer makes carbon cost and reliability observable side by side and automates green defaults. QA evolves test suites to include energy drift and behavior under load. And leadership sets budgets in carbon as well as currency. Then rewards reduction, not just delivery. Now, here is the punchline: when a PM kills an AI feature or an architect rejects a new service, they save more carbon than any downstream optimization ever could. And it was actually the right call anyway. Another point to consider is all of these roles themselves should use AI in the right manner wherever required, in a sustainable manner, to help them in achieving what we have just discussed. So, AI governance beyond the ethics slide. Governance has to be operational, not just ethics slide. Six practices make it real. A model registry, every production model documented with its purpose, training data, metrics owner, evaluation, and sunset data. Data lineage, a provable trail from raw data to features to model to prediction, which DPDP and GDPR require. Bias and fairness gates, subgroup performance report alongside the aggregate, and rollouts gated on it. Real red team practices, adversarial testing from prompt injection, data exfiltration, and model extraction, human in the loop policies, clear threshold for review with an auditable record of the overrides, and independent incident and rollback run books, handling model behavior incidents with the same rigor as security incidents. The EU AI Act has high risk classification triggers exactly this: a mandatory model registry, a risk management system, data governance, technical documentation, transparency, human oversight, and post market monitoring. Practitioners must blind this in or build this in, not bolt it on. This aligns with the EU AI Act and NIST AI Risk Management Framework ISO 42001. And all this requires observability. Without observability, you do not get the information, right? So joint telemetry leads to joint decision. For the AI era, your observability spanned six domains: application, requests, errors, and latency to P50, P95, and P99. The classic golden signals. Infrastructure, talking about CPU, memory, GPU utilization, network, and storage. Cost, you're looking at dollars per service, per request, per outcome. Then the newer ones, carbon and water, grams of CO2 per request and the liters per training run. From cloud provider tools plus Boa Vista and code carbon, model behavior, drift accuracy or monitored cohorts, fairness and hallucination rate, and AI cost of the service, tokens in, token out, cache hit, model used, latency budget consumed. Imagine one dashboard with latency P99, error rate, cost per request, carbon per request, and cache hit rate all on one single page. When anyone regresses, the same on call engineer uses it, and the carbon SLO becomes as routine as a latency SLO. Helpfully, open telemetry now has sustainability semantic conventions and in incubation. So, what is the practical pattern of carbon aware computing? Carbon aware computing is about shifting workloads, not mindsets. Four practical patterns. First, temporal shift. Defer batch and training jobs to low carbon hours, daylight in solar heavy, and overnight in wind heavy grids. Spatial shifting, run latency tolerant workloads in cleaner regions, weighing ingress cost against carbon gain. Demand response, throttle non critical work when the grid signals high carbon or supply stress. And pre compute and cache, do the work during clean hours and serve during peak. Embeddings, model warm up, and common queries. The tooling exists. The Green Software Foundation's Carbon Aware SDK is there, and many other such products, plus the electricity maps and what time APIs. Google has reported internal pipelines that delay non urgent compute to align with grid signals. When published case studies showing 20 to 30% carbon reduction and under 1% latency impact, Carbon Aware isn't anti availability, it's smart deferral. So let us recap and the practitioner's checklist of DevSecOps. Carbon SLOs alongside latency SLO make them visible and page when they breach. One green gate in your CI/CD image size, token budget or region check. Just pick one to start. Policy as code, encode it because slides don't enforce, pipelines do. Joint observability, cost, carbon, latency, and errors on the dashboard. An extended definition of done within carbon and cost budget written down. Extended incident reviews, where did we burn what we didn't need to? Carbon aware scheduling, defer or region shift one workload, measure then scale, and Clarified role ownership. Every role has one explicit sustainability responsibility. Track your team against these 8 items quarterly. The questions matter more than the percentages. Each no is about a quarter's worth of work for one engineer. Turn this checklist into your next quarter's OKRs. So now we come to the last section, the roadmap and the pact, a mature or a capability model patterns from the field, a 90-day plan, and the risks that derail these programs, and the 6 commitments you take back to your team. A practical capability model. First, know where you stand and where you are heading. There are 5 levels. Level 1, aware. Sustainability is a slide, no measurement, no ownership. Level 2, measuring. Carbon, energy, and cost are surfaced for some workloads. Reports exist. Level 3, acting. Targets are in the OKRs, and engineering choices visibly change because of them. Level 4, embedded. DevSecOps gates enforce carbon and data minimization, and the defaults are green. Level 5, regenerative, a net positive contribution, open data, shared models, and ecosystem of uplift. Be honest about where you are. Most enterprises today live between levels 1 and 2. The leap from 2 to 3 looks like this: pick one service, set an SCI target in the next quarter's OKRs, and let engineering decisions follow. That single move can take 6 months, so commit to one upgrade this quarter. So, what are the patterns from the field that we have seen? Here are 3 patterns from the field: illustrative composites with names removed. In retail, an LLM support system routed every customer query through a frontier model. After a cheap classifier first, a small model for 80% of the intents, and the large model only for the complex cases, about 70% lower inference cost and energy, with no measurable quality drop. Second one, in a manufacturing, computer vision ran continuous high frame rate inference on edge cameras around the clock. After event triggered inference plus model distillation going idle when nothing is happening, edge fleet energy down materially and hardware life extended. And in banking and financial services, analytics retrained dozens of models nightly regardless of drift. After drift triggered retraining, a shared feature store, and a smaller candidate models, less training compute, faster and cheaper with same accuracy. The common thread: route complete complexity to the smallest model that can handle it. And don't run compute when there is no work to do. Neither move required new technology, only discipline. Patterns, not promises. So calibrate your own contrast or context. So here is your 90-day practitioner playbook. Day 1 to 30, C, inventory your services, models and data stores, baseline the energy, carbon, cost of your top workloads, and identify the loudest 20%. The heavy hitters, day 30 to 31 to day 60, decide. Set 2 to 3 SCI or efficiency targets in your OKR. Make model right sizing and data minimization your default place, and add one green gate at your pipeline. Day 61 to 90, shift. Shift one carbon aware deployment change, retire one model data set or service that no longer earning its burn, and publish the results inside your organization. Make the win visible. A real platform team did exactly this. Instrumented 8 services, set SCI targets on 2, moved a batch job to a carbon aware window, and retried a duplicate pipeline. Net result: 25% lower compute footprint paid for in engineered days. Cadence beats ambition, small, repeated, measured wins. One important thing that we have to look at is what are the common risks and pitfalls. So let's name what derails these programs. 6 risks. One, greenwashing. Offsets framed as reductions, certificates without operational change, credibility. Vanity metrics, dashboard nobody acts on, PUE without WUE, aggregates without context. Tooling sprawl, 5 carbon tools, 4 data sources, no single source of truth. Founder energy fade. The initiative loses its sponsors and drops off in 2 years. Embed it in the definition of done before it fades. Compliance only stands a box tick mentality that misses the engineering opportunity, treating CSRD as a ceiling rather than a floor. And AI prestige distortion, adopting large models for the procurement narrative while carbon and cost compound silently. The pattern to avoid: a Fortune 500 firm announces net zero by 2030 with a great fanfare. 2 years later, there is no measurement system, there is no engineering KPIs has changed, and no software team can quote the SCI. The announcement was sincere, the operating model was not. Discipline beats the announcement. So now we come to the final pact that you are going to take back to your team. Pick one that you will take it to your team. You can pick more than one also. Uh, So one is think before, I will think before I compute. Two, I will right size a model every time. Three, I will make carbon a first class metric. Four, I will reduce and reuse before I renew. Five, I will share what works with open patterns and open data. And six, I will hold the door open for the next practitioner. You don't have to take all six today. Take one, own it, do it well, and then come back for the next. So that brings us to the end of this program. If you remember nothing else, remember this: sustainable software isn't about doing less, it is about doing exactly enough on purpose. Let's build a quieter, lighter, more thoughtful kind of software together. Thank you spending this time with me. I'm Dr. Niladri Choudhuri, CEO of Excellentro and President of Green Computing Foundation. The numbers throughout the course are sourced from the IEA, the Green Software Foundation, the UN, peer-reviewed literature, and public corporate disclosures. So you can check every one. Now go and make something lighter. Practice sustainable IT and sustainable AI.